This is my solve of the challenge Sudoku set by Cracking the Cryptic. I think Sam Cappleman-Lynes or something set this puzzle. This is not a live solve. I solved this over the week. This video is just me walking through how the solution I eventually found, with help, of course. I'm using my own software here. You can see the URL, at least. You only need to start at this URL, but this is some software I wrote to actually automatically solve basic Sudokus with some variants. I use it for all of my puzzles in a non-automated way mostly. It has some nice features like if you select a number, it will show you, it will shade where that number is visible, which helps you find hidden symbols and stuff like that. And also will automatically clear candidates when you place something. Just the very basics of clearing from the same row in the same box. So let's get started. Let's get cracking, as they say. Let's start with the kilocages. The 29 can only be made from 9, 8, 7, and 5. The 28, well, if we do 9, 8, 7, 4, that's 28. So we can't have 3, 2, 1. So I'm going to say these are everything above 3. Similarly, the 27 is everything above 2. And there we go. Now let's think about where the 1 and 2 is, right? We can't actually place a 1 in the 25. If we placed in the 1 in the 25, we would get 9, 8, 7, 1, which adds to 25, right? Now we can't place a 1 and a 2 in the 25, obviously, so the 2 is going to end up here. Now where can we place the 3? The 3 is not in this. The 3 must be in here, which means we get 9, 8, 7, 3. So this is 9, 8, 7, 1, this is 9, 8, 7, 3, and then this must have a 4 and a 6 because the 4 and a 6 can't go anywhere else. Now if these are 4 and 6, these add to 10, which means these must add to 18. And what that means is the 1 is not in this 25, the 1 is here. Now let's look at the 2. The 2 must be in the 25 sum. Now the only way we can get that is 9 and 8 and 6 and 2. The only way we can sum to 25 with 4 digits including 2. So this is now 9, 8, 6 and 2. Now where can the 3 go? The 3 must go in this, which means this must be 9, 8, 7 and 3. Now where can the 4 go? Can we go in this? So this must be 9, 8, 7, 4. So we have, quite nicely, 9, 8, 7, 5, 9, 8, 7, 4, 9, 8, 7, 3, 9, 8, 7, 2. We go a little further, 2 and 6 can only occur in box 5 in these two, which means that's a hidden double, so this must be a 2, 6, and this must be an 8, 9. Now that we've placed this 1, we can do a bit more. We know that the 3 in box 5 must be in here, so we can eliminate these two. We know the 4 must be here, so we can eliminate these two. We know the 5 must be here, so we can eliminate these two. So now we have all these 7s and 8s, 7, 8, 9s, right? We've got these 7, 8, 9s and 7, 8, 9 x's on the inside, but let's color these 7, 8, 9s because they're going to interact. Now we know we've got 7, 8, 9 here, 4 here, and these can be 2 of them, but there must be a 7 or an 8 or a 9 in one of these two. So let's say one of these is the green one, okay? So these greens knock out these from being green and knock out this from being green, so that's green. These greens knock that out, and this knocks that out, so this is green. So now if we consider similarly, there must be a 7, 8, or 9 here, we're going to call it the blue one. So one of these is blue, which means they can't be blue in that, so that's blue. One of these is blue, means they can't be blue, so that must be blue. And we have pink. One of these is pink, which means neither of these can be pink, even the one that's not blue. And this is green, so it can't be pink, so that's pink, which means that's not pink, interestingly. So this must be the pink. Now, this pink knocks these out, so this is pink. But what we've done here is we've said that this is 7, 8, 9, this is 7, 8, 9, and this is a 7, 8, or 9. This is not the 5. What that means is that this is the 5, which is quite interesting. Now, the next thing we're going to do is we're going to think quickly about these 5 arrows. The way that I can sum to 5 in 2 digits is either 1, 4, or 2, 3. So these are all 1, 2, 3, and 4, all the way around. Okay? Now we're going to do some Piston Phil stuff. So Piston Phil's theorem says that the 16 cells that I'm highlighting in red here must contain exactly the same digits as this ring that I'm drawing here, mostly here. Right, so this yellow ring of 16 digits that has some coloured 7s, 8, 9s in it must contain exactly the same digits as all of these red cells. Now, why does that matter? It matters because we have an 8, 9 here, a 7, 8, 9, 7, 8, 9, 7, 8, 9. These have to exist in the red, but we have 1, 2, 3, 4s. So now we know that the only places that these 8, 7, 8s, and 9s can go in the red is in these 4 cells. So these must be 7, 8, and 9. Now we actually know a little bit more than that. We know that given this colouring, there are 2 greens, 2 blues, and 2 pinks. So we know there's 2 7s, 2 8s, 2 9s, and then an extra 8 and 9. So we actually know that there are exactly 2 7s, and again I'm talking about these cells here. We know there are exactly 2 7s, there are 3 8s, and there are 3 9s. And right now that's not that useful, but it will be later. Another thing that will be useful later is to consider that, alright, these can be 2 or 3 or 1 and 4. These can be 2 or 3 and 1 and 4. But imagine they were the same. Imagine this was 2 and 3, and this was 2 and 3. What would that do to this box? It would totally kill 2 and 3 from all of these, but 2 and 3 can't be placed here. So 2 and 3 both need to be in this element. That's impossible. And what that tells us is that these guys, the combination that makes 5 here is different to the combination that's made 5 here. And similarly, this is different to this. And similarly, this is different to this. So we actually know that we either have 2s and 3s here, 2s and 3s here with 1 4 here and here, or the other way around. 1 4s in the top right and bottom left, and 2 3s in the top left and bottom right. Now all these things are going to be very useful as we go forward. So we can actually do a bit more with this Piston Phil. We've used this theorem to bring these 7, 8, 9s out from the inner ring to these corners. We can use the same theorem to bring these 1, 2, 3, 4s in. So all of the parts of the inner Piston Phil ring that are not 7, 8, 9s must be 1, 2, 3, and 4. Now let's start looking at this 9 arrow. Now for 4 cells to add to 9, where 2 of them can't be the same, these 2 can't be the same, we're going to have 1, 2, 3, 4, 5, 6. We couldn't possibly have 7 because we can't have the other 3 digits add to only 2. Now the outer ones can't be 6 because if this was a 6, the lowest we can get is 1, 2, 1, which is 4, so we have 10. That's too much. So it's a little bit complicated why, but we can actually eliminate 6 from the inside here. Now let's see what happens theoretically if we put 6, 1 in here. What we're going to do, because if there's a 6, it has to be 1, 1, 1 is the only way it's possible. If this is 6, 1, these are both 1. Now what can we put in this sum? We can only put 2, 3, which means this sum is 1 and 4, like we talked about before. If this is 2, 3, this is 1 and 4, but the 1 must be here. And if this is 2, 3, then this must be 1 and 4, but the 1 must be here. And now look, neither of these are able to be 1. These would both have to be 6. So that is nonsense. So we can have no 6 in here. So now that these can't contain 6, if we look at these 5 cells here, they all contain 1, 2, 3, 4, 5, or a subset thereof. Now that is a naked pentuple. What it means is that since these must contain different 1, 2, 3, 4, 5s, there's no 1, 2, 3, 4, 5 here or here. And I'm going to hit this hidden quads button over here, and that just found that a hidden quad is the same as a naked pentuple, so it found those and did that for me. This is just a convenience thing. Anyway, what we now know is a 5 must be on one of these 2. Okay? It tells us a few things. It tells us that there's no 4 here, because 5 and 4 is 9 already. It tells us there's no 3 here, because that would give us 8 here, and then we're too high. So we're either 5, 2 or 5, 1. Now let's imagine what happens if we're 5, 2. it's quite interesting. If this is 5, 2, then this must be 1, 4, because there's a 2 in here, so we can't do a 2, 3. But if this is 5, 2, this and this are both 1. So these couldn't have 1s in them. So this 5, 2, 1, 1 combination knocks out 2 from both of these and 1 from both of these, which means 3 and 4 is the only option left, and that doesn't add to 5. So what that tells us is this is not 5, 2. This is 5, 1. These are 2s. These are not 2s. This is 1, 5. This is 1, 5. And these are 2 and 1. Okay? Now, even better, look at this naked 2, 6. 2, 6, 2, 6. We can have no 2 here. So this must be 2. This must be 1. Now, this 1, 5 in here has taken out that one, but also this one, which means 4s cannot be here. Now, this 2 is taken out this 3, this 2 here, so you must have 3 here. You must have 2 here. Now, what did I say? 2, 3 here means 1, 4 here. No 3 here. 1, 4 here. This can't be 1, so that must be 4. Must be a 1. And since this is a 1 and 4, and this is a 1 and 4, this has to be a 2 and 3, so no 1 here, no 4 here. The 1 we got for this 1, 4 down here eliminated the 1 up here, so we must have a 5 here. We must have a 1 here. Again, we get a 4 over here, we get a 1 up here. So this fun little logic here, the way this 9 interacted with these particular 3 5 sums was quite interesting. It's given us all their values and their placements, and you know, simplified this little 2, 3 here. So there's basics we can do. There's a naked 4. The 4 in this can only be 4. In box 2, this can only be 1. The 3s in box 2 kind of point to this 3, so that can't be 3. Now we take a look at some naked pairs. This 8 and 9, this 2 and 6, this 2 and 3, and this 2 and 3 are all naked pairs. I'm just going to click the naked pairs button up here, and that does those basic eliminations for me. Now the 2 in column 3 can only be placed here. The 3 in column 3 can only be placed here. The 1 in box 4 can only be here. The 5 in box 6 can only be here. This 3 was useful because since we know there's a 3 in this cage, the 3 can now only be here. I'm just going to uncover that. And now in column 9, the 3 must be here, the 3 must be here, the 2 must be here. And I think that's it. Now let's take a look at this 50 arrow. Now we know that since these 3 are different colors, they must be 7 plus 8 plus 9. Let's think about the max sum up from this down, from these 5 cells. So it's 7, 8, and 9. At the max, these two together can be 8 and 9, and this could maybe be a 9. So we have 7 plus 8 plus 9 plus 8 plus 9, which is 41. So the maximum from these 5 is 41. And that means the minimum for these 3 is 9. Now, this 3 here, let's think about what would happen if we placed a 3 at this very top left of the 50 arrow. If we did, this could no longer be a 4 or a 5, because we wouldn't sum to 9 anymore. Which means this is 7, 8, 9, but so now we have a naked triple with these 7, 8, 9s, and this is a 2 or a 6. But since this 3 makes this a 2, this is a 6, so we're going to end up placing a 6 here, which means we place a 6 here. Now if we look at the 5, since we know this is not a 5, the 5 must be here. Now this guy needs to be a 5. It's the only 5 available in this column or in this row. But the 6 is also has to be placed here. So the 6 must be here, and now the 5 can't be anywhere. The 5 and the 6 would need to share this cell. So it's a little bit complicated, but we can eliminate the 3 from here, which means 3 is placed here, and 2 is here, and here, and here. There's quite a lot we can do, actually. But something cool we can do now is let's think about the distribution of the exact 2 7s that exist
in these red squares. We know there's exactly 2 sevens. So if these 2 sevens are on the same edge, the same side of the box, let's imagine it. Let's say this is 7 and that's 7. Then let's think about how we distribute the 8s and the 9s. Let's just say that 8s and 9s are blue and red. So if this is a blue, then that must be a red, and that must be a blue. Since that's a red, this must be a blue, and then that's a red, and then that must be a blue. So having the 2 sevens being on the same edge of the grid forces this diamond pattern of either the 8 or the 9. But the problem is there are now 4 of them. There are now 4 of these, 8s or 9s. And that can't happen. So we know that the 7s are not on the same edge, so they must be diagonally opposite each other. But we can actually go further. If the 7s are diagonally opposite each other, but both on the outside, then we get a similar thing. If this is blue, that's red, so that's blue. That's red, so that's blue, which makes that red, so that's blue. So again, we have these 4, this diamond pattern of 4 8s or 9s, which we can't do. And then the same thing happens if we place the 7s on the inside. We would say this is blue, which makes red, blue, red, blue, red, blue, another diamond pattern. So what we know is that the 7s must be diagonally opposite each other, and they also can't both be on the outside. One must be on the outside and one must be on the inside, like that, for example. Now, the reason we're exploring this now is if we look at 7s in row 3, the 7 must be here or here, and that actually eliminates some 7 options. If a 7 was here, it's going to knock out that option, and it places a 7 here. So this row 3 would now no longer be able to have a 7. So 7 can't be down here or here. Similarly, if we place the 7 down on the bottom left, we place the 7 up here, and we're doing the same thing. This must be a 6, and this must be a 6. So that means 7 is not here, and 7 is not here. Now again, since we know that there are exactly 2 7s, we now know that one of them is these 2, and the other is one of these 2. Okay? So, since the 7 must be here or here, the 7 cannot be here, 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 here. These 2 7s point at that, which eliminate it, but since this one of these 2 must be 7, we can eliminate all of these 7s down here. These 7s in box 2 eliminate that, these 7s in box 1 eliminate that, and that. And that's quite interesting, I think. Now we can also place a 6 in this row. Row 6 must be here. But now let's look at 7s. Since we have a lot of interesting relationships between 7s, let's take a look at 7s in column 7. Now, if we knew that this was 7, then we would know that this is 7, right? If this was 7, it would eliminate pink and green from being 7, so blue must be 7. And if we know that this is not 7, then we would know that one of these is 7, since there must be a 7 in column 7, so blue could not be 7. So if we can eliminate or confirm 7 from here, that's going to be useful. So let's think about what happens. If this is 7, this is 7, we've eliminated this 7 here, which places the 7 over here, which places a 7 up here. Now the only 7 available in box 6 is here. So if this is a 7, all of these highlighted cells are also 7. But we have a problem. This is no longer a 7, this is a 6, and now there can be no 6 at all in box 6. So I'll just draw them in to show you. That's 7, and that's 7, that's 7, that's 7, that's 7. This must be 6, and now there can be no 6 here. So what that tells us is that 7 cannot be down here. Why is that important? Because we now know blue is not 7. and we know that either pink or green is, so these cannot be 7. Next we have some naked pairs, some new naked pairs. If you take a look at this 8 and 9 and this 8, 9, it's going to eliminate 8, 9 from this and these. This is a naked pair of 8, 9s. This is a naked pair of 8, 9s. I'm just going to hit naked pairs again and do those basic eliminations. Now let's think about 6s. And let's think about this arrow, the 50 arrow. Specifically, there's this little triangle of 6s here that says that if these wings, if this is a 6, then that must be. And if this is not a 6, then this also cannot be. Because we have these strong links. Now, if this is a 6, we have a 5, 6 here. This is a 6, that must be a 5. So placing a 6 here, we'll place a 6 up here and a 5 down here. Let's imagine it. 6 is here, we place a 6 here and a 5 here. Now we've put two relatively small values on this arrow, but we still actually can pull off that sum. Until we look a little further. If you take a look at the 5 in box 1, it must be placed here. This must be a 5, and now this must be a 5. And then we're in trouble. The sum of these three is 7, 8, 9, which is 24. We add these, we get to 34. We add this, we get to 40, which means this cell would need to be 10, which obviously it can't be to get to the 50. And all of that means that we cannot place a 6 here, which means we must place a 6 here. We cannot place a 6 here, we must place a 6 here. We must place a 6 here. Now this guy is 7. Now this tells us a lot about 7s. They must be in this configuration. We must have a 7 here. Now look at this in box 4. The 7 must be in this green spot, which means all greens are 7. We don't actually know which one of these is green yet though. But yeah, that's quite useful. Now I think the rest is going to be normal Sudoku things. If we take a look at these 8, 9s, we can eliminate 8 and 9 from this final box here. Yeah, let's just see what we can find. The 5 in this row must be here, which places a 5 here, which gives us a naked 4 down here. 4 must be here, and then there, and then there. Let's place a 7 there. Let's go back to 4s. 4 must be here and here. We've got a naked one here and here. What else have we got? We've got 8, 9, 8, 9. I'm just going to hit naked pairs to do these things. 5, 6, 5, 6, 5, 6. Now let's take a look at this sum here. Because we've got it down really a long way, this 50 sum. We know we have two 7s. We've got an 8, 9, and 8, 9, and another 8, 9. Now, this 8, 9 must be pink, because it can't be green or blue. And in this little triangle, if this is a 5, then that must be a 6, so that must be a 5. And similarly for 6. So these are either 5, 5, or 6, 6. So let's look at the sums we get. 7 plus 7 is 14. Plus 8 plus 9, I'm just going to 7 plus 7 plus 8 plus 9 gets us to 31. Now we can either add two 5s here, 5 plus 5, and then a 9 up here, and that could work. But what if we added two 6s? If we add 6 and 6, we would get 43 as the sum that excludes this, and this would have to become a 7, which it can't be. So that means these can't be 6s. These must be 5s. That must be 6. There's more to do there. But we also know that pink now must be 9. So we've placed these 9s, and we've actually placed all of the 9s. Which means we've placed all of the 8s. All in one go. We've placed the 2s here. We've got 3 here and here. We've got 6s here, here. We've got 7 there, 5 there, and we're finished. I'm going to hit the check button, Yep. The check didn't check the sums, but if we take a look at these sums, 7893, I'm gonna uncolor this 4. 7894, 7895, 8926, like we said. These sums are all set, and this sum, just to check again, I'm going to do 797, 9855, 7 plus 9 plus 7 plus 9 plus 8 plus 5 plus 5 is 50, so everything's good. Now I got a lot of help from the Discord server on some of these general strategies. I got some helpful hints. I'll give attributes in the comments about the people who gave me a little bit of guidance in solving this. But there you go. I think this was a very difficult and very interesting puzzle, and I enjoyed doing it. So thank you again to Cracking Cryptic for showing it to us.